Good afternoon to everybody and welcome to this event organized by IEEE Student Branch. I am Nancy Pavianiti, a PhD student, and I am the treasurer of Women in Engineering Affinity Group of the IEEE Student Branch of the Politecnico di Torino. Today, I will introduce you the engineer Antonio Manzalini from TEAM, who will present the seminar entitled Future Internet, a bridge from artificial intelligence to quantum intelligence. And this is possible thanks to the IEEE Distinguished Lecture Program, which aims to help young students and young researchers to provide suggestions on their research problems and more in general on their future careers. We would also like to thank the engineer Tiziana Tambosso, who helped us to organize this event. And finally, I want also to say thanks to all of you that are following our event via YouTube streaming. And for this reason, to make the event interactive, I invite you to expose your questions and curiosities with a comment in the YouTube streaming and in all of our social channels, such as Instagram, Facebook, and after the web seminar, I will report your questions to Antonio for more clarifications. Well, okay, now it's time for Antonio. So good vision and enjoy the event.
Thank you very much, Nancy, and good afternoon to you all. Thanks for participating. Well, first of all, I wish thanking again IEEE Italy section for the prize and for supporting this this event. I would like thanking also Polytechnic of Turin for hosting and organizing this this venue, and also my company team for allowing me to make this talk. This is the essence of the lecture I wish making today. In a nutshell, we are witnessing today a progressive diffusion of ultra broadband connectivity, both fixed and mobile. Also, the deployment of network and service platform based on cloud and edge computing, and also the boom in artificial intelligence, not only for providing services and embedded in applications, but also for the operations of the telecommunication infrastructure. All of this for providing new digital services for our daily lives. This is what we are calling the digital transformation of the society, of the industry. It's a big revolution we are facing today. If you look at it, at least metaphorically, it looks like we are, let me say, embedding a sort of nervous system into the reality, because we have this wide adoption of terminals, devices, smart things for the Internet of Things, which is sensors, which is allowing us to collect an enormous quantity of data, the big data sets, increasing exponentially every year. Data which are transmitted by these ultra broadband fixed mobile connectivity links with ultra low network, with ultra low latency networking functions, transmitted to cloud and edge computing data centers. And this is way the processing, the enormous processing and storage resources are elaborating and storing the collected data in order to infer decision with artificial intelligence, which then can be actuated by actuators. So it's a metaphor, but described in this way, this is the feedback loop of any autonomic and nervous system. So that's why I said, in a certain way, we are embedding a nervous system into the reality. In order to make this model sustainable as we wish for the future, on the other hand, there are big challenges we have to face. The transmission and the processing of this enormous quantity of data transmission with ultra low latency, elaboration in almost real time to close the loop efficiently. We need to think about lowering energy consumption, obviously, taming the complexity of the infrastructure, which is more and more pervasive and more heterogeneous in its device. The need of increasing the resilience of the infrastructure of the internet, the security, the privacy, a lot of issues behind the sustainability of this model. At the same time, we are facing some roadblocks or some bottlenecks which we have to manage. For example, electronics, the well-known Moore law is saying that electronics is probably starting facing some fundamental limits. So in this overall picture, which I've summarized very, very quickly, today we are detecting a growing interest, which is pretty interesting, and several investments from industry worldwide about quantum technologies. Somebody is arguing that these quantum technologies could allow us to make a quantum leap in order to make this model sustainable for the future, meeting the requirement of the challenges we have to face. So in this talk, basically, we will look at that, the intertwining of the evolution of telecommunication, ICT, internet in general, the evolution of artificial intelligence, and the potential exploitation of quantum systems. Is really coming a technology breakthrough, or are we just talking about, as we said, food for techies? This is the big question we are facing today. I'm not saying we will have an answer to this, but we will start discussing about that. So this is the slide showing an interesting feature news. I stumbled upon a few days ago on Nature. It's an interesting article where Nature analyzed the commercial deals in the field of quantum computer and quantum communication in general, cross-referencing details of a number of quantum startups and industries published in market research websites and consultative reports. And well, what is emerging, I recommend you reading the feature news. It's quite interesting. You see the source at the bottom of the page. There is a growing number of quantum technology firms which are raising cash from private investors, particularly in the sector of quantum computing and quantum software. You see the infographic on the right-hand side of the slide. While on the left-hand side, you see the growing interest in intellectual property rights on quantum. Quantum patents are growing exponentially from the analysis they have made since 2012. It seems that China, it's not a surprise, is dominating, at least in quantum communication, but North America is ahead on quantum computing. Well, these are interesting signs, probably, of a trend. We are also detecting daily a number of press releases which are announcing increasing efforts and increasing investment in innovation activities. We have notable examples in Microsoft, IBM, Hewlett-Packard, Toshiba, Google, Intel, Alibaba, Tencent, Baidu, but there are also network operators and several startups in academia and centers of excellence. It's interesting that according to the World Economic Forum, quantum technology are expected to have far-reaching implications of our society, impacting more than 50 sectors of our industry, of our society in the near future. But there is always a reverse side of the coin. Somebody is arguing, for example, there was this report of US National Academy of Science, Engineering, and Medicine dated December of 2018, warning that if early quantum computers won't emerge soon with profitable uses and use cases and field trials and commercial application, concrete commercial application, probably the field could face a sort of winter, as the winter we have faced with artificial intelligence a few decades ago. whilst today artificial intelligence is flourishing. This picture is just to showing some of the selected investors betting on quantum computing startups. You see there are also network operators, for example, SK Telecom and Deutsche Telekom investing on ID Quantique in Europe, but there are several other players making investment. And there are a lot of international initiatives, not only private initiatives. I wish mentioning here, for example, the initiative from the European Commission, which has launched 1 billion flagship on quantum technology starting in 2018, with a number of projects funded within the program Horizon 2020. China announced plans for spending more 10,000 billions to build national laboratory in the quantum fields, opening this year. And by the way, this has triggered the effort, they say, from US to create a similar initiative in the US. And as a matter of fact, recognize this potential impact of quantum technology to US government has enacted recently a legislation to coordinate and accelerate US quantum research and development. So it seems there is a plan. So let's go a little bit more in detail. But before that, let me spend a few words summarizing some definition, just to align a little bit the language. You know, quantum technologies are already here today. Should not be a big surprise. They have already transformed our daily life. Even today, computers, smartphones, the camera of the smartphones, the medical imaging devices, the lasers, these superconductors, components, all these devices are basically working on the inner behavior of quantum particles, of atoms, governed by the rule of quantum mechanics. We should not forget that. But what is happening today is that the emerging generation of quantum technologies, what they are doing today in quantum technologies, pretends to go further in manipulating the quantum phenomena. And strange, let me say, quantum phenomena, which are known as superposition and entanglement. I'm sure you have heard of this phenomena. They are quite strange phenomena, at least from our Galilean perspective, but in a few words, superposition is a phenomenon in which particles seems to have multiple states until they are observed. And entanglement describes the properties, some properties of the quantum system, such as the spin and polarization, can be strangely intertwined together. We'll come back to that later on. This is just to say that these new, well, they are not new, they are known since decades in quantum mechanics, but today quantum technology pretends to manipulate this new phenomena, superposition and entanglement, for a number of applications, which are basically, let me summarize, in 4 domains, which you see in this slide. One domain is the domain of quantum communications, where individual or entangled photons, or let me say qubits, are used to transmit data in a probably secure way. Quantum computation, which employs the quantum effects, the quantum phenomena, superposition, basically, to speed up computing, passing from exponential time to polynomial time. Then we have the area of quantum simulations, where well-controlled quantum systems are used to reproduce, to simulate the behavior of other, more complicated or less accessible quantum system, and then quantum sensing and metrology, which is also very promising, where the high sensitivity of coherent quantum systems is exploited to enhance the performance in measurement physical quantities. This is a very advanced area. We have very amazing sensor based on quantum phenomena, which have already been exploited in military applications. But let me start from some definition, as I said before. So, as a digital system manipulates bits, a quantum system manipulates qubits. So the qubits is the basic unit of information, of the quantum information. A qubit, can be coded in as a quantum system in two states, two levels. For example, imagine an electron. The spin of the electron could be spin up or spin down. So we have these two states. Or just imagine coding the qubit with a single photon. You may have a vertical polarization or horizontal polarization. So, but the most remarkable difference between bit and qubit is that whereas a bit is either 0 or 1, a qubit can stay simultaneously with two values, 0 and 1. Strange enough, this is the so-called superposition of states. And this superposition is maintained until it collapsed. For example, when we make a measurement or when, unfortunately, some noise is making it to collapse. So if you want to see it a little bit from a mathematical viewpoint, we can say that a qubit could be modeled, could be seen as a linear combination of two states, 0 and 1. You see on that picture on the right hand side of the slides, as a linear combination of two states where the coefficient C with I of this combination, linear combination, are complex number. This is the secret. This is the most important point. The fact that these coefficients are complex number is allowing us to make operation leveraging on the interaction between quantum states in terms of constructive and destructive interference, as much as like we have in waves, in fields. So, in other words, we can say that one qubit can be in the superposition of two states. It goes that two qubits can be in the superposition of 4 states, and so on. 3 qubits can stay in the superposition of 8 states. So the remarkable point is that while an bit, traditional bit, can take one of the 2 to the power of n possible permutation, and qubits can stay in the superposition of all the 2 to the power of n possible permutation. And it's a sort of parallel processing, which we have here with quantum computer. And that's why quantum computer can be much more powerful than digital computers, solving problems in shorter times, from exponential to polynomial time of computation. I don't want to enter into many technical detail as time is running, but what I'd like saying is that allow me please to simplify a little bit. Processing with a quantum computer is like playing with the probabilistic computing, but instead of having real number for expressing the probability, we have complex number. Actually, quantum algorithms elaborate complex numbers referred as amplitudes. And complex numbers, you know, can also add up in ways that cancel with each other, in the same way as we have the destructive and the constructive interference when two waves or two fields are interacting. And the Eulero formula is helping us is understanding better the story. At the bottom of the picture, you see the way the quantum gates are basically operating, making matrix multiplication of complex numbers. Yes, because quantum gates are the equivalent, quantum logic gates are the equivalent of the digital gates, which we have for the traditional computing, and they are the building blocks you see in this picture of the quantum circuit. Yeah, we have a great number today of quantum algorithms already developed. I would say, in approximation, obviously, that most of these algorithms are coming from two best-known algorithms which have been defined, invented in 1995, which are the Shor algorithms for factoring and the Groover algorithm for searching. Most of the algorithms we have today, quantum algorithms today, comes from the combination of these variants or variances of these two algorithms, even if there are other algorithms such as quantum random walk. But the important story is that today we are already using these algorithms also for a number of very interesting applications which have in our infrastructures, for example, for optimizing the planning of 4G and 5G infrastructure. This is actually an achievement of recent achievement of TIM, or for solving combinatorial problem in wireless communication. So let's now have a look at the state of art. If we want to somehow elaborate about the initial question I put on the table with this talk, we have to have a look at the state of art to understand what's going on. Well, you have heard surely a number of press releases saying that quantum supremacy has been reached. Let me say that, well, quantum computer is true that today are getting more and more powerful, incredibly powerful. But for reaching the quantum supremacy, plenty of qubits are not enough. You know, the random fluctuation of it or from any quantum mechanical strange process could occasionally flip or randomize the state of the qubits we are talking about previously, potentially derailing, creating errors in the execution of the quantum algorithms, in making the quantum calculations. So even if today we have this exponential growth of the processing power of quantum computers, a great part of the computing power, I'm not saying the most of it, but a great part of the computer power goes to correcting errors and not to running algorithms. So let's have a look at the state of art, how they wanted to solve this bottleneck, because this is one of the main bottlenecks that quantum technologies are facing. So this picture, I enjoyed very much this picture because it's showing a sort of classification of different areas where the state of art of quantum is moving today. We have the area of superconducting circuits for general purpose quantum computing. We have topological systems, photonics systems, quantum annealers, the area of quantum software and quantum consulting, etc. Let's start from the superconducting circuits. So let's start from the area of general purpose gate-based quantum computing. So there are remarkable achievements from technology providers. One example is Intel, which is working since 2015 with QTech, an advanced research center in the Netherlands. And remarkably, Intel announced at CHES 2018 a 49 qubit processor. You see on the right hand side of the picture, which is based on superconduction, so superconducting qubit. You know, this is a property, a physical property of electrons. When properly cooled down, the resistance of the material goes to zero, and the behavior of a number of electrons becomes condensate as it were a single electron. So I've already said a problem here, a challenge here, which is cooling. Superconducting chips needs cooling to avoid the coherence, to avoid that it will derail the calculation. It's interesting looking at this picture from the Intel website, the timeline they see for quantum computing. They say we are in the system phase, and the commercial phase, which is starting, according to their opinion, from 2015 on. So in five years, which is, 5 years is quite a short span of time for potential really big revolution in technologies. Google, I'm sure you've heard of it, recently announced they have reached the quantum supremacy. They published the story in a nice paper on Nature. You can find it in the source at the bottom of the slide, and the company blog. They say they have developed and tested this 45 qubit quantum chip, quantum computers named Sycamore, allowing them to reach the quantum supremacy, solving very complicated problems only in, well, this is the press release, in 200 seconds, while the world's fastest supercomputer could have taken a lot of years, let me say. They are making huge investments. Also, the Quantum Artificial Intelligence Laboratory of Google is working on that. Recently, they have also announced Bristlecon, another chipset optimized for quantum intelligence. This is something that will again pick up later on. Rigetti is another technology provider, a startup, which is much more than a startup today, which is working on a 128 qubit chip. You see, a lot of qubits. We pass from the announcement of Intel 49 to 54. Google, now we are talking about 128. Again, it's superconducting qubit computing. But the interesting point is, I think, well, at least in my opinion, is that Rigetti is offering a platform called Quantum Cloud Services for allowing researchers, anybody, to access their quantum computer for making experiments. The users may have access to their own dedicated quantum machine image, which comes preloaded with all the necessary tools. This is something also which is shared by IBM. Also, IBM is offering a cloud-based platform, which is called IBM Q Experience. You can access it and making experiments, developing your own quantum algorithm and quantum gates before. And this has been unveiled in CHES 2019, where they announced this Q System 1, saying that this quantum computer is a formal step before commercialization of quantum services. A lot of work. Well, this presentation obviously is not exhaustive for lack of time. There are other important technology providers which are making impressive achievement in the same direction. I want to spend a few words about topological computing, that's where Microsoft is investing. We mentioned previously that the fragile nature of qubits is one of the most significant hurdles or roadblocks to be solved for technological breakthrough in quantum computing. And Microsoft is looking for the breakthrough addressing the development of topological qubits. You know that topology, worth Nobel Prizes in physics recently, is a field of physics with concrete applications, physics and mathematics, where an object can shift its form, being stretched, bent, unfolded, maintaining the same properties. So the idea here is using the topological properties of quantum particles to make the qubits more stable against noise, against heat, against other strange phenomena, quantum phenomena, which could derail the quantum computation. It's something like, let me say in a few words, splitting electrons in quasi-particles, Majorana fermions, but I'm not in the position to enter in technical detail, but you can Google and find more information about that. Google is moving also in another direction, which is not too purely technological as the former one I've described, but also in the direction of developing ecosystems. So partnership with a number of other technologies and other provider to develop an ecosystem on top of which building the services of the so-called Azure Quantum. And you may find many other pieces of information and details Googling the URL. Let's move quickly to D-Wave. D-Wave is well known. It's this time it's a special purpose computer. It means that D-Wave cannot run the Shor's or the Groover algorithms we have mentioned previously, or the circuits you may want to develop with quantum gates, but D-Wave is solving problems with the technology of the quantum annealing. The quantum annealing is a sort of meteoristics for finding a global minimum of a given objective function of a set of potential candidates, candidated solution. And it's like thermal annealing fundamentally, but in this case you're using the strange phenomena behind quantum computing, for example, the tunneling. There are a lot of cooperative agreements made by D-Wave with a number of industries for several applications. Let me move quickly to the quantum computing based on quantum optics and photonics, because this is really another emerging and very promising area. Psi-quantum is one of the remarkable startups working in this direction. The idea here is using the photons for coding the qubits. So photons are more stable than superconducting electrons. So using the technology of silicon photonics, a breakthrough might be possible in shorter times. Also, Tundra Systems is another startup betting in this direction, using quantum optics, using photonics to develop quantum computing. Well, we know that very well that quantum optics, optics has been around for decades until now, and it has been used. It is used for laser transmission of optical fibers, also for cross connection of signals in optical cross connect. But quantum optics is something more. Is a research and innovation avenue addressing the interaction of the quanta of light, the photons, with the atoms, with the molecules. So it's somewhat like I said before, the quantum optics and the photonics technologies today are pretending using the quantum mechanics superposition and entanglement phenomena to exploit at affordable price new functionalities which we don't have today in optical communications. It's like quantum mechanics applied to photons beyond the classical electromagnetisms. It's not Maxwell equation, it's much before. It's quantum electrodynamics of Feynman. So you can make a jump in the future and imagining quantum optical networks as not simple quantum networks as we have today based on WDM, wavelength division multiplexing nodes, add-drop multiplexers, optical cross-connect. But extending this traditional architecture, exploiting real quantum phenomena. I've tried making a sort of overview of the state of art and analysis of this potential jump in the future about quantum communications in this paper. You may want to have more details. You can take a look or drop me some questions about that. Another problem is in area, which is, and here the border is blurring with what I've said previously, is overcoming the limitation of today quantum and tomorrow classical computing with optical processing, using light, using electromagnetic signal, much more than classical electromagnetic signal, also seen from the quantum perspective, to make processing. I will not enter into details, but I'd like giving you some ideas, some flavors. You know that in artificial intelligence, in machine learning, in deep learning, matrix multiplication, vector to matrix multiplication is the most important operation you have to carry out. But they are time consuming first, and importantly, energy consuming. If we project to the future, the expectation which we have for artificial intelligence, we have also this exponential growth in terms of processing time and energy consumption. So this might be a problem for sustainability. So the question which this startup, Light-On, but also other remarkable startups and industry are addressing is, how can we make such operations, such matrix multiplication in the optical domain directly, saving time and saving energy? You know, the Fourier transform, the optical Fourier transform can help in this, importantly. And so that's what they have developed with this startup, Light-On. They developed a sort of optical processing unit, which is using light for making calculations, exploiting the properties of the optical Fourier transform. And it goes per se that this optical processing consumes much less power and the speed is much, much higher. Well, let me add something which is even more challenging, which is the idea of using metamaterials and metasurface to make optical processing, to make quantum computations. It's possible. I'll show you some example. The next slide, just a few sentences to say what are metamaterials. Metamaterials are materials containing inclusions to control the electromagnetic field, impinging them at certain wavelengths. And these inclusions are made of metals, dielectrics, they could be active elements, pin, diodes, varactors. So basically, with metasurfaces and metamaterials, you can control the electromagnetic field, you can control light, and so you can make calculation, you can make processing, you can exploit the quantum mechanic properties of light. And very recently, you say the date is March 2020, Howard published on Nietzsche physics this amazing paper showing how they developed and tested quantum metal surfaces to do that, to do optical processing, controlling the behavior of atoms, controlling the behavior of the electromagnetic field at the quantum level. And they claim in the paper that this could be a breakthrough for quantum computing. There are also other examples you see in this slide where a strip of metamaterial can execute the Groover algorithm. That's really impressive. Let me jump quickly to the next box in this map of the state of art of quantum technology, which is quantum software. Well, software for quantum computer has different point of view. Well, you know, there are at least four dimensions which we should address when talking about software for quantum computer. Understanding if we are talking about discrete variable gate model quantum computers, which is the basic definition of general purpose quantum computing. Remember the beginning of my presentation. Continuous variable gate model, which is very promising. There are interesting European projects in this direction for the quantum key distribution systems. In this case, the qubits, we are not talking about qubits, we are talking about Q modes, which are continuous variables. So it's a paradigm which is closer to the thinking of quantum field theory, which is closer to quantum optics, quantum electromagnetisms. Another area is adiabatic or quantum computation. D-Wave is an example. That's another approach we have to take when talking about software. And then we have the area of quantum simulators, which we have mentioned previously. So just to say, when talking about quantum software, well, we have to understand in which domain we are moving. Anyhow, if you want to have a global picture, you can take a look again at the paper from Nietzsche, which I've quoted at the very beginning of my presentation. They've made an analysis demonstrating that quantum software is an area which is attracting an impressive number of investments, with about 20, more or less, firms raising something like more than $100 million across around 30 deals in the time span from 2012 and 2018. These numbers are providing just as the flavor of what is going on, but there are several startups which have raised millions and tens of millions of dollars. You see at the bottom, I'm mentioning Zapata Computing in Cambridge, Massachusetts. 1QBits, which is collaborating, by the way, with Microsoft in Vancouver, and the well-known UK-based Cambridge Quantum Computing. So let's jump to quantum application and services. The time is quite limited, so I will just make a quick fly 10,000 feet. As I said previously, the strange phenomena behind quantum mechanics, which is being used today by quantum technology, could lead to application in four main areas: communication, computation, simulation, and also quantum sensing and metrology. By the way, there is an interesting roadmap from European Commission that you see in the link on the right-hand side of this slide, where you can have a look at what Europe believes is, at least for the quantum technology community, a roadmap in this application area. One application area is, we have mentioned previously, artificial intelligence. Just imagine how the area of cognitive computing, artificial intelligence could be improved if using the enormous, at least in principle, processing power of quantum computers. You see, I'd like a quote in IBM Watson CTO recently saying that a revolution like this could amplify artificial intelligence capabilities by order of magnitude. As a matter of fact, today there are several field trial and use cases with industries. I've mentioned here in the slide one example, but there are several others from Daimler, for example, in using quantum artificial intelligence for solving very complicated combinatorial problems in the context of smart city, not only for solving the problem, obviously, but also for learning in almost real time how to behave and to react quickly to changing conditions. So it's true that quantum computing means more processing power, thanks to the presence of this phenomena of superposition of qubits, allowing us to move from exponential to polynomial processing time. This is one claimed area of application which could radically improve the performance of artificial intelligence. But as I said before, we should not forget that there is more. It's possible to develop artificial intelligence, machine learning, computational model based on photonics, based on quantum optics, using the optical Fourier transform for making very complicated matrix multiplication in one CPU clock cycle. There is a paper, a very interesting paper from Nature, which I quoted here, where you can take a look at the state of art of quantum optical networks and quantum artificial intelligence. Again, if you wish, I've made a paper here summarizing a little bit how quantum optics can disrupt the deep learning artificial intelligence in the future. You may take a look at the paper if you like, or just dropping me a call or an email. Well, another area which is very important, very amazing, is the quantum communication, the quantum internet. I'm sure you've heard about the teleporting of qubits. That's, again, something strange based on the previously mentioned phenomena of quantum mechanics. The teleporting of quantum information is about the transmission of qubit without any physical transfer of the particle storing the qubit. That's a little bit unbelievable, but it's a property that probably we could not explain it, as Feynman say, today, but it's a property of nature. So why don't we exploit it? Why don't we use it? In this case, we're talking about the entanglement. Unfortunately, the entanglement is very fragile because it can be degraded by noise. But again, if we use in teleportation the optical qubits, if we use photons for as qubits, it's much less fragile. And so it might be very promising for medium-term application of quantum communication, of the quantum internet. There are bottlenecks, clearly. There is the problem of developing the so-called quantum repeaters. We have a theorem, no cloning proof theorem, which is apparently forbidding us to clone quantum information, but there are workarounds, very, very interesting publication. I'm quoting one of my friend Kalefi and Kachapuoti, presenting very promising approaches to solve these bottlenecks. Well, if we look at the security area, well, quantum key distribution is one of the most discussed and promising application of quantum technologies today. Quantum key distribution explains the fact that the mere fact of observing a quantum object perturb it in a reparable way. So that's the secrets for the security coded in the reality, in the basic functionality of quantum mechanics. Today we have commercially available solutions of quantum key distribution system based on a protocol which is named B84, which are exchanging the cryptographic key. So basically here, the quantum technologies are used to generate a quantum key, exchange in a quantum channel, which is then used to for the cryptography of the digital information. The protocol is very simple, is in 4 steps. I don't think I have time to go through these 4 steps. You can take a look at the slides later on, but basically I'm using photons. I'm using the polarization of photons. There are already deployments or field trials in a pre-commercial states of quantum key distribution system. This is what is claimed by SKT, where they are claiming to use this pieces of equipment from ID Quantique. If you remember at the very beginning, I mentioned that Deutsche Telekom and SKT are investing on ID Quantique, which is the startup in Europe developing and commercializing these systems. SKT is deploying these systems on their LTE network, and they are planning to deploy it very quickly, they say, in their 5G system for offering quantum security as a service. In Europe, we have remarkable examples of field trials and experiments from BT, which is joining other technology providers and universities, research centers, to participate in the UK Quantum Network, Quantum Initiative. Again, one of the nearer goal of this initiative also for BET is security, as it is for Telefonica in their experiments in the metropolitan area of Madrid. They've made recently some experiments and very interesting publication on that. In Italy, we have the so-called Italian quantum backbone, where a number of institutions, INRIM, CNR, and others are joining to develop this backbone along the country. I can provide you further details later on. Just one more slide to say that quantum key distribution could be used also for satellite communication. Actually, in China, a joint cooperation, China-Austria, use the quantum key distribution B84 protocol for providing secure communication across satellite links. There are also ongoing some standardization activities. I'd like mentioning just a few of them. In GSMA, for example, we have recently set up a group working on quantum technologies and services. In this group, which came from proposal from team together with other operators, SKT, Orange, Deutsche Telekom, AT&T, Verizon, Telefonica, but also some technology providers such as Ericsson. This group, industry group, is looking at the delivery at the end of October 2020. So we are working today on that, a document to to draw the overall background of the status of quantum technology, to understand what is the technology readiness level. In this activity, we won't go into technical details, but we want to understand the state of art and the concrete exploitation of field trials of technology in lab, out of lab, and the industrial perspective. We want to identify the challenges, the business opportunities, the roadmap for delivery quantum services. SKT, for example, is announcing that they are ready to develop quantum security as a service of a 5G infrastructure. So let's understand how integrate quantum systems, whatever they are, quantum key distribution nodes or quantum computers or quantum repeaters or quantum optics pieces of equipment in current infrastructure, because there is also a problem of understanding how integrating these pieces of equipment in the current infrastructures from the management viewpoint, from the control viewpoint. We cannot pretend to develop new parallel infrastructure based on quantum technology. If a technology breakthrough will come, we have to mitigate with the legacy infrastructure. Other standardization activities are carried out by ITU, where we have a focus group on quantum information technologies for networks. In IETF, where they have set up a quantum internet research group. That's why at the very beginning I've mentioned future internet. Quantum technology are expected to impact also the evolution of the internet, not only telecommunication, obviously, and ICT, but also quantum internet. And quantum safe cryptography is one of the area of investigation since a few years ago by ETSI. So I think that today, and I am approaching the very end of this presentation, it's quite difficult to define the technology readiness level of quantum technologies. But we want to investigate in that direction. Industries investigate in that direction. You see in this picture just an example of a guess recently made with the positioning of the various quantum computing device in this, ranking of technology readiness level. So let me jump to the conclusion. So we said that there are several evidences of an increasing efforts of industry in innovation activities and in making investments on the quantum technologies and quantum services. A future breakthrough at affordable price of these technologies may have systemic and far-reaching implications in several application domains. It might be a very big change of paradigm. It might be much more radical than the digital transformation. The areas for sure will be several of them. World Economic Forum arguing 50 social and industrial sectors. We are saying ICT, telecommunication and internet, artificial intelligence and security will be three areas where we could easily guess an important impact. Obviously, there is a reverse side of the coin. There are bottlenecks, there are roadblocks, there are problems to be solved. There might be the risk of a quantum winter, but we should carry on. This is what's going on, in investigating what's going on to realize what the real level of maturity. And a first flavor, at least what I perceive from this analysis, from the discussion we have with our peers in industry, but also in academia, in research center, in startups, is that we need, there is a need of pursuing a systemic and shared approach for describing the whole stack. Okay, that's all from my side. Thank you very much for your attention. Now I'm leaving the floor to Nancy, I guess.
Yeah. Thanks for the explanation, especially for the very interesting proposed topic. Now let's start with the questions. And the first question, Vincenzo asks, how do you think will quantum computing and AI affect security?
Oh, well, security, we know even today, which we are crossing, the so-called digital transformation, is one of the hottest areas. Resilience, obviously, privacy, but security is one of the most important areas where we are focusing efforts. If quantum computers will be developed at affordable price, they will express such an impressive processing power, which would allow them to crack our cryptographic key. So it's a big risk, it's a big threat we have to face. That's why the technology advances in quantum key distribution is providing some answer to that risk, the risk that the power of the quantum computers will have the chance of cracking current security system. Regarding the second point, well, as I said, let me add one more sentence. As I said, there are some players, network operators, which are already claiming today they are ready to provide quantum security services across their LTE and 5G infrastructure in order to, provide an answer to this risk, to this threat. Going to the second part of your question, even today, artificial intelligence is used for security with several applications. So we can imagine the use of quantum intelligence also for, providing more powerful quantum secure services, which we have today also in digital infrastructure. I mean, having an artificial intelligence which is amplified in its capabilities with quantum technologies, as I've mentioned previously, for example, we can make more robust security system even for today digital communication. One example is the use of quantum holography to develop images which can be used as a quantum cryptographic key. I hope I've answered your questions. Thank you.
Okay, at this purpose, Ilaria asks, can quantum computing threaten the security of cryptography, hash functions, and in which way?
Yes, that's, I think, basically what I've mentioned in the previous answer. If you exploit the quantum computing capabilities, powerful capabilities, which are, reducing the processing time from exponential to polynomial, you can for sure crack our cryptographic systems. That's a risk which has been pointed out, stressed by ETSI, the European standardization body, already a few years ago. So should quantum computers be available at affordable price, they can be used to crack for sure the current digital cryptographic key. And that's why industry is looking at quantum key distribution to overcome this potential threat. So I think I've answered also previously at the same, more or less the same question, if I got it correctly at least.
Okay. And Sarah asks, what would you advise a new PhD student who want to dive into this field?
Oh, well, this field is really amazing. I wish to be a PhD student to get the opportunity to enter in this domain. Well, there are these 4 areas which are very interesting. All of them: quantum communications, quantum simulations, quantum computing, and quantum sensing, and metrology. I can tell you my personal opinion. If you look at the short-term application, you should consider quantum security as the area of application where a lot of research is still needed beyond the BB84 protocol, but that's where we will see concrete near application. If you want to look more at the future, you could take a look at the quantum optics communication systems. So the area of quantum communication where you can make quantum teleporting of information. But this is more on the long term. For example, we have a problem there, which is how developing quantum repeater, how overcoming the roadblock posed by the no-cloning theorem. It goes per se that there are several applications in the quantum computing domain which might be interesting for a PhD. You have seen there are several technology providers, and Intel, D-Wave, Rigetti, plenty of them working, Microsoft working in these areas. That's quantum computation. But also quantum sensing and metrology, where it seems there are a huge investment from Defense Ministry. So that's where probably we'll see also important breakthrough in terms of quantum sensoring.
Okay, Eduardo asks, when do you expect we will have a QKD secured cellular networking in Turin?
Oh, well, I don't know. That's a good question. I don't know when, honestly, we will have this in Turin. I can say that quantum key distribution, a few words about quantum key distribution, repeating what I've mentioned before, some players are claiming they're ready to provide quantum security mobile connections in the very near term. It's SKT, and that's what we are debating in the GSMA group. Probably after this discussion, we'll get a clearer picture. They are using ID Quantic. I don't want to make any advertisement of this pieces of equipment, but it's just to mentioning that there are commercial pieces of equipment, but there are commercial pieces of equipment or pre-commercial pieces of equipment also from other important technology provider. When looking, nevertheless, let me add something. When looking at quantum safe communication, we should not focus only on quantum key distribution, but we should consider also maybe a simpler area of application, which is very promising as well, which is the quantum random number generators. There are random number generation which are really quantum based, So they could be used. Actually, there are already experiments ongoing in using them to ensure to make a quantum secure connection for the Internet of Things in the future. But this is just my guess. We may imagine having an application on our mobile phone using an optical, a quantum random number generator to create a quantum security key to cryptify our information. This is the technology readiness level of this is quite high. I mean, probably it's a matter of making experiments and testing it, because there's a nice paper about that. I can provide you the link if you like. The most simple and unexpected device which could be used as a quantum random number generation is already there in our mobile phone. It's the camera of the mobile phone. They have demonstrated that the camera of the mobile phone can be used to generate truly quantum random number generators. So I could imagine an application developing a quantum security key to provide a quantum secure connection for mobile phone or for smart things in the Internet of Things. But we should consider also this perspective, which is very amazing.
Okay, and Luca asks, what are the physical conditions to make quantum photonic systems work? Do you think that such conditions will limit the use of quantum computers in applications?
Well, let me go back to my slide on on quantum optics and quantum photonics, which was my first love at the university, at the Polytechnic of Turin. I made a thesis on this topic, so I think it's my first love. So quantum optics, as I said, provide us the opportunity of developing quantum processing, quantum computing, using photons to code qubit. So if you use photons and you're not using superconducting qubits, which are electrons, which have to be cooled, photons are more stable. Photons today are already used apart the photons which we transmit with the radio links, because they are still photons. We use light photons in the optical fibers. The only things, well, not the only thing, but let me simplify. The most important thing today is realizing that the photon, when the photon is coded in qubit, it has a number of degrees of freedom, which is really much more than the polarization. Today we are using only or mostly polarization, but we have several degrees of freedoms which we can use. Some of this degree of freedom are shown in this picture. Is the spin angular momentum, is the optical angular momentum. So if quantum optics and photonics will be able, and there are already demonstrations in fields, quite mature, I would say, manipulate this degree of freedoms, then we will have not only quantum computing, but also quantum communication based on quantum optics and photonics, which are very stable and don't require cooling, because cooling is something which we need when handling electrons, superconducting electrons. Superconductivity is the lowering of resistance of a material approaching to the absolute zero, which is minus 273 degrees. I hope I've answered the question.
And the final question of Mohammed. says, which technology could be better to apply for machine learning, especially on the image processing problem? Annealing or universal quantum computers?
Well, it depends actually on the applications you are going to develop with your artificial intelligence system methods. My personal opinion, but that's really my personal opinion, is again betting on the use of optical processing and the use of exploiting, let me say, a very simple property of the Fourier transform in optics. When you use the optical Fourier transform, amazingly, you can make, in a very simple way, matrix multiplication, saving a lot of time because it's done at the speed of light. You don't require cooling because you use photon, and saving a lot of energy. So I think this is very, very promising to be considered for short to medium term application. But it depends on the application. I mean, also quantum annealing is very promising, as we said. For well, quantum annealing is used already today for solving several optimization combinatorial problems. Thank you.
Thank you, Antonio, and I want to say thanks for your availability and your enthusiasm for taking part of this event.
Thanks to you.
I would ask you stop the share if you can.
Sure.
Okay.
Thank you.
We'll send you by email the certificate of participation, with the hope of hand delivering it as soon as possible. And before leaving the meeting, I would be pleased if the engineer Tambosso want to intervene. Okay, thanks.
Thank you. Do you see me?
No.
Not yet. Okay, this way.
Yeah.
No. Thank you. Hi, Antonio. Hi, everybody. I'm pleased to hear. I would like to thank Antonio for his beautiful presentation. I have also a lot of questions for you, but I don't know if there is enough time for that. Only one. I would like to ask the technological level of readiness of super computing using optical quantum computing respect to the supercomputing based on superconductivity material. So what are the one respected to the other, the level of technological development, the difference between the two?
Well, that's a very difficult question to be answered right now. Again, probably at the end of our work in GSMA, where we are set up this group with other industry to scan what are the proof of concepts, experiments, real field trials, benchmarking the performances, blah, 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 blah. Probably by October, we could provide you a more meaningful answer. Now I can tell you my personal opinion. I've shown you during the presentation a picture at the very end of my presentation, showing that the technology readiness level for some of the current quantum computers based on superconducting are ranging from 4, 5 to 8. 5 for IBM, Google, Rigetti Computing, 8 to the D-Wave quantum annealer. So it seems that quantum computing based on superconducting technology, at least based on these analogies, based on the evidences which we have today, is quite high, at least for the wave, is at a medium level for IBM, Google, Rigetti Computing. I would say it's lower for the most disruptive technological approach I've heard here, which is the one on topological qubit from Microsoft. But we know that Microsoft is also working with other of the above mentioned technology provider of quantum computing. Concerning optical quantum computing, in my opinion, the technology readiness level is quite high. It's today is again ranging from, I would say, 6 to 8, because basically you see there are already some startup providing since 2018, if I remember correctly, optical processing units which are using light, which are using quantum optics processing capabilities to support, to be integrated with CPU and GPU. So basically they are claiming already that today they are selling pieces of equipment based on this technology. But again, looking at the what they are doing in the research labs and in the startups, basically we are handling photons. So the most important roadblock which we have in quantum computing is the story of the coherence, is the story of the error corrections. You won't have such big problems if you are coding qubits with photons. So that could be something which is really disruptive, bringing the optical quantum computing to higher levels in the technology readiness level. That's at least my opinion.
Thank you. It's also my opinion, because I think that I agree with you. I think that the superconductor based quantum computing has the drawback of the temperature, because they have to work at a really low temperature. And it's not the case for optical quantum computing. So probably for future applications that are available for normal people, for us, optical quantum computing will be more interesting than the others that probably will be used by big companies, big data, in big companies. In fact, there are big companies that are interested in the development of this supercomputing quantum superconductor computing. Okay, this is my opinion, but we will see. We will see. We hope in 5 years really to have something. This is a really a good news to have something ready in 5 years, because there are really many years that this quantum computing is studied. From optical quantum computer are studied till I think 1980. The first papers on that. So it's really. We are close to the end of this story. Thank you, Antonio. Thank you so much. Okay. I am expected to say some words about what we are doing now in the section, because one is one of the events that we organized. Antonio is the winner of Industrial Distinguished Lecturer Award 2019 And this is one of the programs or awards that we have in order to connect our members, in this case students, but these lectures are open to all members, with the industry. And this is an important program we have that connects important people and researchers coming from industry with their experience, real concrete experience, what is cool in the industries, and the world of research, both in academia and the students, PhD students level. So, but we have also other programs in the section and other cooperation with the industry, also awards. You can find that in our sites, and also some important events, conferences that are that see the cooperation of our section, but so an association like IEEE, academia, and industry. One of that is the forum that is Research and Technology for Society and Industry, RTSI, that unfortunately this year, due to COVID epidemic, has to be moved from September 2020 to September 2021. And this is really a pity, but we prefer for this particular event to have the possibility to have a face-to-face conference instead of electronic conference, especially for this kind of event that is not only a typical technical conference, but is a real forum with a strong technological part, the state-of-the-art presentation of invited speakers and the papers on the most important topics, but it includes also events with the participation of students, young professionals, and industry representatives. And so for this reason, we move this year, this conference, and to the next year. But if you want to see more details about the events of the section, you can find on the web that is always updated with the information. And we have several events organized by the section this year. We have also another conference that is a Melecon. Unfortunately, this is the case, Melecon should be organized this year in Palermo on June. And due to that, we can move to another year because we have already received the paper, evaluated the paper. So for this reason, Melecon 2020 will be given in a virtual way, electronic, like an electronic conference. And this epidemic changed a lot of things, and also the way we can manage. We try to do our best to give service to our members, as is this conference that is made in this way. I thank you so much, the student branch, because they were very active in organizing this event with the possibility to have also a YouTube registration of the event for other members that would like to learn about this very interesting topic. I thank you again, everybody, the speaker for the really interesting presentation, and the organizer for the perfect organization of the event. Thank you so much.
Thank you. Thank you again, Engineer Tambosso, for your suggestions and your help for the event organization. And at this point, I want to thanks to everybody for questions and curiosities. And thanks to Antonio Manzalini and Tiziana D'Ambosso for their presence. And thanks to everyone for the time spent with us. So see you soon and stay safe. Bye.
Bye-bye.
Bye-bye. See you soon. Stay safe, please. Bye.
Stay safe. Take care.
Take care.